So welcome everyone. Thank you for joining. My name is Justus Bogner, and together with Philip Iljewski, we are scientific coordinators at the DISC here at the Digital Sustainability Center, which is a center of excellence under the umbrella of the ASI, the Amsterdam Sustainability Institute. And we do a lot of things, but one of those is outreach and events. And this is one of those events. So we started a series of distinguished lectures where we invite experts from around the world on certain topics that give talks here at the FU that are hopefully interesting to a lot of people in the department. And I'm very happy to welcome Marijn Heule from Carnegie Mellon University in Pittsburgh in the States. But he started his academic career actually in the Netherlands. So he has a PhD from TU Delft. And before going to Carnegie Mellon, he also was an assistant professor at the University of Texas in Austin. So his research, which he will talk about later, he focuses very much on solving hard combinatorial problems in areas such as formal verification, number theory, but also extremal combinatorics, whatever that is. And more specifically, he is an expert on Boolean satisfiability solving. So he has developed several award-winning SAT solvers and uses them often to resolve famous mathematical conjectures. And I'm sure we will hear a bit about this in his talk. So with that, the floor is yours. Marijn, thank you for being here and looking forward to the lecture.
Thanks so much for the introduction. The sound is working? At least, okay, perfect. So it's great to be here back at the VU. So what I'm going to talk about is solving mathematical challenges using symbolic AI, and one already kind of went, okay, what's symbolic AI? So I will predominantly focus on satisfiability solving, but that things become clear. So if you now read kind of the major newspapers these days, almost every week there seems to be an article about AI for mathematics. Mostly the tone of these articles is that AI is going to take over the jobs of mathematicians. I doubt that is actually the case, but I do see there's a lot of potential for this technology, especially if we combine it with the knowledge of mathematicians. And the results I'm going to talk about, they also, most of that, there's a lot of input from mathematicians to actually make it work. But what is one of the excitements also about mathematics is that in order to get AI right, mathematics seems to be kind of the perfect playground. And why is this the case, right? You cannot just do a lot of hand-waving stuff and hallucinations. For mathematics, you need to get the details right. And especially symbolic AI, which is logic reasoning, where we can validate everything efficiently, will be crucial here. And especially if we combine this with formalization, ideally auto-formalization of the original problem, we can have a very end-to-end trust. Although the movement is relatively new about AI and mathematics, there actually is a very long history in computer-aided mathematics. I could easily have shown actually 60 years, but one of the early very known examples where computers were used to solve a mathematical problem was the four-color theorem. So if you have a map, and if the only constraint is that adjacent areas cannot have the same color, can you always color it with four colors? Then there's also the Keller conjecture regarding the optimal packing of cannonballs or oranges, about Rubik's, the optimal strategies to solve the Rubik's Cube. And what you see here on the slide, in recent years, more and more problems, some of them that were open for decades, others were open for over a century, have been solved using computers. And in particular, there's something that they have all in common, is that all of these problems have been solved using a satisfiability solver. So how many of you heard of satisfiability solving? Okay, almost all of you. So that's very good. So I do give a brief explanation, but the cool thing here is that all these problems, satisfiability solving, which is kind of the key in automated reasoning and symbolic AI, is was required here. Now, so most of you heard of satisfiability solving. I give you a very brief kind of introduction. So what is satisfiability? It stands, it asks, given a propositional formula, does there exist an assignment such that the formula evaluates to true? So this research started in the early 60s. And in the first kind of 35 years, there was steady progress, but we could only solve, say, in the mid-90s, formulas with thousands of variables and thousands of clauses, which is still pretty big considering the potential search space. But the breakthrough that we had in the last, say, 25 years really allows us now to solve for many problems, problems with millions of variables and millions of clauses. If you want to know more, feel free to reach out, but there's the Handbook of Satisfiability, which is 1,500 pages on the topic, where Ed Clark calls it a key technology of the 21st century. And also Donald Knuth wrote, as part of the Art of Computer Programming, officially it's just a subsection of the book, but it's 360 pages on the topic. Now, just to make sure that we're all on the same page, so it's a propositional formula over here, and it consists of 3 clauses. And so I use this for the or, this for the and, for the not, and this for the and. And so we have a formula consisting of 3 propositional variables and 3 clauses. And if we want to know whether there exists an assignment such that evaluates to true, the most naive thing that we can do is we can build a truth table with 2 to the power n being the number of variables, assignments, and then we can see that there exist 2 assignments over here, P, Q, and R. So P false, Q false, R false, true. That makes this true, and the same holds for the opposite assignments. But of course, we are not going to make a truth table because there's no way we can build a truth table for 2 to the power, say, 1,000,000. So we need something else. And there has been, that something else has been satisfiability solvers, which have been competing with each other. Sometimes even over 100 solvers have been competing during the annual competitions. They started in 2002. And what do you see over here? So we see over here the winners of the competition from 2002 to 2020. So it's the name and the year they won. On the left, what we see is a cumulative distribution plot. And what we have over here is that this is the time in seconds, and this is how many benchmarks from the 2020 competition the solver could solve if this would have been the time. And so what we see here is, for example, that the 2002 winner could solve slightly over 50 benchmarks. Kisset, the winner of 2020, could easily do this in say 100 seconds. And so what you also see is that almost every year you see that there is progress. Somebody comes up with some new idea to kind of improve the performance on some problems. And so you see that overall, every year you see big improvements, and especially so the solver Kisset, right? You see enormous progress. There was, for example, in 2020, and we have seen also in recent years a lot of progress. So these solvers become stronger and stronger, and problems that were unsolvable the year before can now be solved using this technology. And what we are now going to talk about is we're going to, so these problems come from all kinds of different applications. I'm now going to zoom in on how can this technology be used to solve mathematics. Now, let me start with a problem that was over a century ago. So Schur asked the following question, and this was back in 1912, and he actually solved it in 1916. So we have all the positive integers, and will any coloring of the positive integers with 2 colors, let's call them red and blue, result in a monochromatic solution of A plus B equals C. So he just didn't ask it for 2 colors, but for any color, any finite number of colors. And so what I show here on the slide is the solutions A plus B is C with A, B, and C up to 5. Now, without loss of generality, if we have 2 colors, we can assume that 1 is colored blue. If 1 is colored blue, 1 plus 1 is 2. 2 needs to be colored red. Yes. So that all of the numbers have the same color. No. It cannot be the case that all 3 of them are the same color. Okay, so you can yeah, that's the only restriction. Yeah, no, but you should avoid. So we're trying to find a counterexample, right? So will any coloring of the positive integers result in a monochromatic solution? In order to refute it, right? We want to find, is there a coloring for which we can avoid it? Yeah. No, you have to find a coloring of the numbers 1 to 5 such that for all these 6 sums, there is at least one of them is blue and at least one of them is red. Yeah. So since 1 plus 1 is 2, and since 1 and 1 are already blue, both, 2 needs to be red. Yeah. Now, since 2 plus 2 is 4, 4 needs to be blue. Yeah. And since 1 plus 3 is 4, 1 and 4 are blue, so 3 needs to be red. 1 plus 4 is 5, so 5 needs to be red. But if they're both red, then we have all 3 of them red. So no matter how we color, so the only assumption I made is 1 is colored blue, right? But blue and red are interchangeable. So no matter how I color them, we always have a monochromatic solution. So this is for 2 colors. Schur showed that this actually for any finite number k, there is a number sk known as Schur number k, such that if you put the numbers 1 to sk, avoid the monochromatic solution. But if I try to color the numbers 1 to sk plus 1, there's no way to avoid it. Yeah. And so this is what Schur showed. So for any finite number of k, there exists such a Schur number k. And he also showed that Schur number 1 is 1, Schur number 2 is 4. So that's also the example I give over there. And Schur number 3 is 13, which is also doable by hand. But already Schur number 4, it took Baumert almost 50 years later to show that Schur number 4 is 44. Right? So this was also one of the early computer proofs. And in the 2018 paper, I showed that Schur number 5 is 160. So another 50 years in between. And it wouldn't surprise me if it takes another 50 years to actually show that Schur number 6 is whatever it may be. Right? So the search space becomes harder and harder, and we need more and more advanced technology. What I also did is I produced a proof, and I will talk about proofs more later on. But the proofs was substantial in size, 2 petabytes. For those who are not familiar with petabytes, so this is 2 million gigabytes. So it's substantial, but we have formally verified checkers, and I will talk about that later, that can check this efficiently. So we can have high confidence in the correctness. Yes. No. So it is an argument that covers all possible colorings, but without talking about all possible colorings specifically, because the search space here is 2 to the power 160, right? Or right, 61. right? Actually, so you have to show that 2 to the power that 161 is impossible. So space is 2 to the power 161, and this is closer to, what is it, 2 to the power, what is it, 55 or so. So you can have a much smaller search space. Now let's look at a quite related problem. So we just looked at monochromatic solution of A plus B is C. Now we're going to look at the monochromatic solution of the equation A squared plus B squared is C squared with 2 colors. And on the slide, I showed you the solutions A squared plus B squared is C squared for ABC up till 40. And it's very easy to do this by hand to make a solution that doesn't have any monochromatic solution. And even up to 1000, 2000, you can almost do it by hand because it's very easy, because there's so much freedom. So a decade ago, the best thing so far was that you can do the numbers 1 to 7664 without a monochromatic triple. And Myers actually in his PhD thesis conjectures that you can push it to infinite, but that the problem just gets harder and harder. Now, how do you translate this into propositional logic? So at least for this problem, it's very easy. And so similar to what we did for Schur number, we try to find a counterexample of a limited size. For Schur number, we had 1 to 5. Now we're going to say from 1 to n. And how are we going to translate it into propositional logic? For each number in the range, we have a new propositional variable, pi. If pi is assigned to true, it means I is colored red. Yeah, I is assigned to false, I is colored blue. Right? And now for each Pythagorean triple, A squared plus B squared is C squared, we have 2 clauses, one stating that at least one of A or B or C needs to be red, and one stating at least one of A or B or C needs to be blue. Now, so you can just do this in a couple of lines of C code. You can just generate this formula. And we showed in the 2016 paper that you can color the numbers 1 to 7,824. Actually, with the right local search, you can do this now kind of in a minute. But you cannot go beyond that. The first time we solved it, it was 4 CPU years, but 2 days on a cluster, because the nice thing is that we can heavily distribute things and have linear time speedups, even with thousands of cores. And also we produced a proof here that was 200 terabytes in size, and which we validated using a formally verified checker. And I come back to that later. Okay, so both Schur number and the Pythagorean triples, it's a very natural way to translate these problems into propositional logic. But the really cool thing here is that there's all kind of problems now out there that are resolved using this technology, that it's not so clear that, okay, how are we going to translate this into propositional logic, and how are we going to use these kind of tools to do this automatically? Let me talk about 2 such problems now. So the first one that we solved in 2019 is Keller's conjecture. So what is Keller's conjecture? Keller's conjecture is a tiling problem. So you need to tile, say, the infinite, so the 2D plane with all tiles that are exactly the same size, square tiles of the same size, and you cannot have any gaps. And the question is, can we make a tiling such that there is not 2 adjacent ones that fully share an edge? Right? If you think about tiling the 2-dimensional space with square tiles that are all of the same size, then the only way you can do it is you put the tiles into lanes. You can shift the lanes arbitrarily from each other, but 2 adjacent ones in the same lane fully share an edge. Right? Now you can ask the same thing about the 3-dimensional space. So you have all unit cubes and you want to fill the entire 3-dimensional space without gaps. Is it possible to do that such that there's no 2 cubes that fully share a face? So on this picture over here, I try to do this, and at least the three faces that you see over there, the only way to continue is to put a cube there that fully shares the face that is blue, right? And so if you give it a little bit more thought, then you will figure out that it's slightly more complicated in the two-dimensional case, but you cannot avoid this. Now, is Keller's conjecture? So Keller says, okay, it doesn't only hold for dimension 2 and 3, but it holds for every dimension, right? So more precisely, for every n larger equal than 1, a tiling of the n-dimensional space using n-dimensional unit cubes, there's always two adjacent ones that share an n-1 dimensional face. And so the interesting thing is that the conjecture holds for dimension 1 to 7, but it breaks at dimension 8 and up. And so, we in the 2019 paper, we solved the final case, which was the n equals 7. And we used, so we translated it into SAT, which, okay, how are we going to do this? Because this seems kind of not something, a continuous tiling problem is kind of a complicated thing to do in propositional logic. But luckily, there was a lot of math behind it to make the problem discrete and to make sure that we actually could translate it into satisfiability. Now, another problem which I was able to solve recently, which I also didn't expect this to be possible. So what we're now going to look at geometry, and we're going to look into what kind of shapes emerge if you put points in the plane, with only restriction that you cannot put 3 points on a line. And in particular, what we're going to look into is the shape a K-hole, which is K points in convex position without a point inside. So this was studied by Esther Klein already in the 1930s, and she showed a very nice argument that you need 5 points. Every way you put 5 points on a piece of paper, there always are 4 points in convex position without a point inside. So what is her argument? Her argument is there's only 3 cases. Either the 5 points are on the convex hull. If that is the case, then you just pick any 4 points, and they are 4 points in convex position without a point. Right? The second case is that the convex hull consists of 4 points, and there's 1 point inside. Now we can take one of the 2 diagonals, and then we take those 2 points. We take the point, there's 1 point on one side of the diagonal, there's the point inside, and together those 4 are 4 points in convex position without a point inside. And the third case is that you have the convex hull consists of 3 points, so there's 2 points inside. You draw a line through the 2 points, and there's always 2 points on the other line, and so you take those 2 points and the 2 points inside. So this was known in 32. Again, there was another 50-year gap to kind of make progress here, is that you need 10 points to have 5 points in convex position without a point inside. And a really surprising result by Horton in 83 is that you can always avoid 7 points in convex position without a point inside. So he made a construction with infinitely many points that have no 7 points in convex position with a point inside. Yeah, so every way you have, and so in the early 80s, there was only one case remaining, which is the empty hexagon, the symbol. And this is what we did. So which is 1.5 years ago, which is showing that you need 30 points to have an empty hexagon. Now, okay, how do you kind of approach such a problem, right? So, of course, we cannot talk about the reals, right? And so we have to abstract the problem. And so how do you translate it into satisfiability? We're going to have for every triple of points, without loss of generality, we assume the points are sorted from left to right. And what we're going to do, we have a variable, a propositional variable, OABC, stating that if we draw a line through A and B, then C is either above or below the line AB. If we have these variables, many of the assignments that we can make are unrealizable, but luckily there are a lot of constraints that you can add to the problem that remove many of the unrealizable assignments. Additionally, we can express using HABC variables, so that I won't go into detail here, but you can express using the orientation variables whether a triangle of A, B, and C is empty. So these are kind of our key ingredients that we have, but then there's still many sub-translations possible if you make this kind of encoding, right? And that has a big impact on the performance. And actually, there have been almost 10 years, people have been looking into this geometry and using these kind of encodings to try to tackle the empty hexagon problem. And they were not able to solve it. But I figured out how to make this translation, which were able to solve it. And I do think, but we can maybe also talk about it at the end, that learning can be really helpful to kind of guide non-experts. Okay, so the key such a translation, and I want you to give you kind of a brief insight in how can we solve such a problem and what is the key thing to make it work, right? So the key thing, so the question that we have is, so how many variables do you need to assign to ensure that there is an empty hexagon, right? And so given 6 points, how many empty triangles with these points guarantee an empty hexagon? That is kind of what you use in the encoding, and what the mathematicians did that tried to solve it. They said, okay, what we're going to use is we just make sure that if there's 10 specific triangles, because there are 20 among 60 points, if there are 10 of them that are empty, namely all of them that includes the leftmost point, then we guarantee, no matter how the points are sorted, of all of those triangles empty, then we for sure know that we have an empty hexagon among those 6 points. Yeah. But in case you want to put this as a constraint, so with the H variables, these are clauses of all length 10. And the solver has quite some difficulties reasoning about this. Now, what I changed, the key thing that I changed is, okay, they had not used the assumption that the points are in convex position. So with assigning 4 variables, you can force that the points are in convex position. Now, when you enforce that, how many triangles do you need to know that are empty to make sure that there is an empty hexagon among these 6 points or others? So that's a good guess for anyone else. So this is also what I thought first for. And this is also initially what I implemented. But it turns out it's 1. And this is kind of, and so actually the solver actually quickly found it out. And so I kind of later, if this triangle is empty, so you skip always 1 point. So if this one is empty, right, then there are the other 3 triangles. So either they are empty, or there's a point inside one of these triangles. But if there's a point inside one of these triangles, then we can replace the point that we had with one of those. So for example, if there's a point over here, right, then we can replace b by b prime, right? And thus we can keep doing that until there is an empty hexagon, right? And so what we achieve with this is that we can actually we know that 4.4 variables assignments give us convex position and one empty triangle, so we can get the clauses from length 10 to length 5, and that makes the search space significantly smaller and really helps to solve, right? Because as soon as you know that a triangle is empty, that really forces a lot of puts a lot of constraints on the other points. Right? And so this was key to solve this. And actually, the interesting thing is, so because I implemented exactly what I said, so initially I had the other triangles there as well, and then what I noticed in the proof of the solver that it in the beginning really discarded the triangles when A and F, so the leftmost and rightmost points, were close. And I was thinking, why is it quickly discarding that? And then I figured out this argument. And then, of course, I put it in general, because if the points are far apart, the solver cannot easily deduce it. But of course, this holds, of course, arbitrary of whether the points are close or not. Okay. Any questions to this point? Yes. Yes. So I don't. So actually, I will talk about AI proofs now, or proofs now. But for Keller, we actually have lean from first specifying the whole problem and then the subproof. So we have an all end-to-end argument in lean. So we first had the subproof, and then I got 5 PhD students at CMU that 5 weeks or so were able to formalize in lean. Yeah. Yeah, so so the only hard work is in coming up with the right encoding. So for this problem and several of the others, I just use, although I slightly changed heuristics, but that maybe gave me 10 or 20%. And given that it was 2 CPU years, that doesn't really matter. This encoding got us from, and the right splitting got us from 100 CPU years estimated to 2 CPU years. So the key thing is so automated reasoning. So reasoning is automatic, but you have to get it into the right form in order to get the real performance. And so this is the key thing that makes it more difficult for non-experts to use it. And this is also one of the things I'm trying to address with some of my students. Yeah. 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 So so you have so for 4 points you don't need to have anything. For 5 you need 1 square triangle. For 6 you need 1, and for 7 you need 2 triangles. Yeah. 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 But for 7 the problem was it was already known that for 7 that you can avoid it indefinitely. Yeah. Yeah, so the key challenge is always how to encode it such that the solver that you get max performance out of the solver. But which solver, it doesn't really matter. But at least if you take one of the, say, the top 5 solvers from the competition, then they all work pretty well. also changing the heuristics. The solvers are really good into managing it themselves. So, but the key thing is how to get the encoding in the right shape. Such a counterexample, not, but you might see patterns that you kind of find larger and larger ones. But already given that this would be 30, right? It might take quite some time before you figure out that there is that you can generalize such a thing. So I think that would have been much more of a challenge, yeah. And but also, although I don't have a kind of a slide on this here, but Tim Gowers, a Fields medalist, he so when he about the Pythagorean triples, he calls it the most disgusting proof ever. I'm not sure what he thinks about the even larger proof of Schur number 5. But I spoke with him about this tech, and I said, okay, don't you like this technology? He said, yeah, I like the technology, but I don't like how you use it. So because I don't like it that you run things for years and CPU years, and then the answer is no, right? But he says, what I like, and that I've also been helping others with that, and that's also much more of also now of interest, is to provide counterexamples or examples for mathematicians to kind of guide the intuition. And so that can also, the same technology can be used for that. No, I don't know applications now or was pursuing. Yeah. Okay. Yeah, no, I have not really looked into that aspect, but it was so it was more that I kind of was fascinating kind of that after this problem that Esther Klein started kind of 100 years ago, that there was just one case remaining that I wanted to kind of tackle. Okay, now let's talk about proofs. Because I think, so especially if you run things for years of computation, it's only natural to doubt the correctness. So when I first solved the Pythagorean triples problem, I put it on archive, and then a couple of days later, there was an editor from Nature who contacted me and for an article, and I tried to explain to her what I tried to explain to you, that this is really cool technology, that we can really trust it, and that we can have linear time speedups. None of that made it into the article. It was just 200 terabytes. It's the biggest math proof ever. It's kind of a dubious honor, right? Because you can just make the heuristic slightly worse and the proof will become bigger, right? So it's not really an achievement, but it got a lot of things, including all kind of things, comments like 200 terabytes, it's for the PlayStation 4s, and so on. But what are these proofs? So, and I think this is not only for automated reasoning, but I think a very cool idea in general. So if you want to have trustworthy software. So what is the case? So we have, say, a formalized statement, and we want to kind of give it to a reasoning tool and then provide our outcome, right? But as my colleague Randy Bryan says, that as soon as a program has more than 40 lines, it's very likely to be buggy. When we have talks about SAT solvers, they are many thousands lines of code, so very likely to be buggy. And so can we really trust the results? And so I'm now talking about math problems, right? But these tools are mostly used in industry to show the correctness of hardware and software. And you don't want to have a claim of correctness be based on a bug of the tool, right? And so, and in case there is a bug in the tool, actually you have to kind of rerun all of your kind of experiments, that all your correctness claims, to be sure that it was not a bug that made the claim. So one thing to deal with this is to formally verify the solver, right? But there are several issues there. It's hard to develop. Formally verified tools are typically much slower than the non-verified ones. And it's very difficult to make it scale. And these solvers are constantly being changed. And so if you have a proof of correctness and you made some update, I mentioned that the solvers are improved every year, you have to constantly change the proof. So this is not really feasible. But what's the alternative? And this is actually really nice. So what instead we're going to do is, so this solver is highly complex, right? But what we're going to do is we're not just producing the outcome, but we also produce a proof in a with much more simple steps. And then we can check whether the outcome and the proof match. And so whether we can have to fully check whether the argument holds. And the nice thing is that we can, with very limited overhead, say about 5%, we can produce a proof. And especially since we have now on laptops and everywhere, we have always kind of a spare core, we can do actually the proof checking concurrently and actually have no effect kind of on the performance. Check that all of the outcomes are correct. Yeah? And so the tool might be buggy and probably is buggy. But as long as you know that you can verify the result, you know at least that the outcome that you care about is correct. Right? And ideally, and this is also what we have now, is that we have these checkers that are much more simpler tools. And not only are they more simple, they are formally verified and they don't change. They don't need to change. Right? And they are very efficient. And so we can, with the checkers, we can make sure that all of the outcomes that we have, we can trust them. Right? And this is much more, so we only have, say, 5% overhead, and then we can have fully trustworthy outcomes. Yeah. I will come over. And yeah, but I will try to make it accessible, but it's the hardest thing on the slides. But I will come to that. Yes. Yeah, no, but so ideally, but this is not only ideally, so it's maybe for other, but so we actually have now formally verified, efficient formally verified checkers in all of the main theorem provers kind of, and not only, so we have from ACL2, Isabel, Kok, KML, and Lean. And this is now the practice, right? So we don't care about the correctness or the completeness of the solvers anymore. We only care that they produce a proof that we can check. And I spoke to various developers of the solvers, and they said that since we're using these proofs, which is now we do now for about a decade, they make the solvers much more exotic and kind of crazy kind of reasoning, because it was in the past, it was really difficult to get it right, but also the proofs are great to debug your tools. Right? Because as soon as something goes wrong, you can easily kind of check where things went wrong. And so have full confidence in the results. And also industry now, when they use satisfiability solvers or SMT solvers, especially so they just always check now the results, because it's such a little overhead and it gives you now guarantees that you can fully trust it. So then this is, I think, a very important idea that goes way beyond satisfiability. So kind of SAT made it kind of really prominent, but I think in other areas, if you want to have kind of trustworthy tools, this is a very key technique. Now, there's your question. So this is by far the hardest slide on the most technical one, but I do want to give you kind of an impression of how these proofs look like. Now, because people that know a little bit about SAT solver, heard of it, they think the tools is just doing brute force but then it's highly efficiently implemented using some good heuristics. That's kind of how people see it, but there's more going on, and it might have been the case until the early 2000s. But there's so much exotic reasoning going in the tools that you have you can prove that there are lots of exponential speedups compared to any kind of brute force methods. So how does these proofs look like? And so the cool thing is that there's only one rule. I don't put the formal rule here in, but it's actually relatively easy to formally verify and to easily implement, also in a formally verified checker. But what is the rule kind of saying? So what it's saying that for every assignment that would satisfy the formula, but falsify a given constraint, that can be repaired into another assignment, tau prime, that would satisfy the formula and the constraint. If that's the case, then adding the constraint to the formula preserves satisfiability. Yeah, especially kind of this would satisfy, it sounds like maybe a bit strange, but maybe also kind of another formulation is, so if you have an assignment that falsifies the constraint, but that assignment also satisfies or might satisfy the formula, then if you do any repair to make sure that the constraint is satisfied, that repair doesn't change that the assignment satisfies the formula. Yes. So we repair is that we change the assignment such that it satisfies C, because initially it falsifies C, but it keeps satisfying gamma. Yeah, so you make some changes such that C now becomes satisfied while not falsifying gamma. If tau would have satisfied it, right? But the thing is, we are only kind of more interested in most cases for this when gamma is unsatisfiable. So there is no assignment that would satisfy gamma anyway. But the thing is that the check is that we can keep things local such that we, under the assumption that the assignment would have satisfied it, then we can make changes to it that after the changes, it would still satisfy it. But there's typically no such one. But let me give you kind of an example. Oh yeah, and the key thing here is that the validity of the repair needs to be checkable in polynomial time and typically actually in linear time. But the requirement is in polynomial time. Now let's look at an example which is actually satisfiable, but maybe to give you kind of what goes on in these solvers. So we have this formula over here, P or Q and not P or not Q. And this is our constraint, P or not Q. So the only assignment that satisfies the formula but falsifies the constraint, right, is P to false and Q to true. And this can be repaired by making P true and Q false. And therefore, gamma and C are equisatisfied. And so what this rule can do is it can add clauses that if it was satisfiable, removes satisfying assignments, although it always guarantees that if it was satisfiable, there's at least one satisfying assignment left. It is all kind of tricky, and so I probably need a dedicated lecture for 1.5 hours to really kind of explain what goes on. But I just want to give you an impression that, okay, how do these proofs look like? It's all, so the proofs are simply a sequence of constraint repair pairs ending with the empty clause and ending with the empty repair. And so what you do is, so you get such a pair, you check whether the repair is valid, and then you add the constraint to the formula. And then you keep doing this, and if you can add at the end, then you know that the formula is unsatisfied. Yeah, and so we have this sequence of pairs, and just we check validity of each of the repairs and then add it, and then that's it. And then at the end, we conclude that the formula is unsatisfying. So let me, because I have a larger example here. Afterwards, maybe that makes it more clear. Yeah. So which is the mutilated chessboard problem. So what's the mutilated chessboard problem? We have a chessboard and we take away the opposite corner cells, and we ask whether the remaining grid can be filled with dominoes that cover exactly 2 cells. So on the left, there's an empty mutilated chessboard. On the right, I tried to fill it and I didn't succeed. Can anybody tell me whether this works? And why not? Exactly. Opposite corner cells on a chessboard have the same color. So if you take them away, then there's a color imbalance and you cannot do it. Right? This is a very nice argument, right? But the problem is, of course, if we would give this problem to a satisfiability solver, then it would run along, so 8 by 8 is easy, but say for 25 by 20 or 26 by 26 is much more complicated, right? And why? Because we don't give it the chessboard pattern, right? So it's this nice kind of, and it kind of makes it kind of intuitive and gives you the nice argument, but the solver is just tries all kind of options. One of the things I observed is that it's very difficult for a computer to find the nice human arguments, such as the chessboard, right? Because it's really so humans know about chessboards and they come up with this nice argument, but this is very difficult. However, what I also observed is that almost in all short, nice human arguments, the solver also figures out a nice argument. But that argument is typically quite different than the ones that humans come up with. But it's also somewhat understandable. So let me explain you what goes on here. But first, going back to this one rule. So, because what is the solver actually doing when it tries to solve this problem? So what it tries to do is, and so when you say, okay, there is the issue over here, right? Although it's actually, the dominoes do not match that picture. But so if there are 2 horizontal dominoes on top of each other somewhere, right? Now what the solver is now doing is that now assume we can satisfy everything else. So tau somehow satisfies everything else. We know it's not possible, but under the assumption that it would be satisfied, right? Then there exists another assignment where we keep tau, except where the 2 are replaced by 2 vertical at the same location, right? And so we have another solution. And as a consequence, the solver figures out that throughout the board, we can kind of assume without loss of generality and produce a proof of this using these taus and the repairs. Say there are no 2 horizontal dominoes on top of each other. So we just changed the problem from, okay, we can put dominoes everywhere into, okay, we can put dominoes everywhere, except we cannot put 2 horizontal dominoes on top of each other. And so, again, this is not possible to satisfy it, right? But under the assumption that we can do it, then we can replace the 2 vertical ones by 2 horizontal ones. And we can do the same thing with, if there's 2 vertical ones and 1 horizontal one on top, we can always replace them by 2 vertical ones and 1 horizontal one below. And the solver can figure this out using these taus, and so this kind of reasoning. And if you block both pairs on the entire grid, then the number of cases goes from exponential to linear, and then you're quickly done. So there is another short linear kind of argument here, but it uses something that we can understand, but it is something completely different. Right? But this is something that it can all do locally. So the chessboard pattern is some global property. This is all local. It figures all out that, okay, locally we can replace by two and things like that. And so the solver is automated reasoning, I sometimes say, is kind of local reasoning because it's really good in doing things locally. And it's very difficult to come up with something globally, but frequently when there is a global argument, there tends also to be a local argument. And the solver can find that one. So I don't know whether that kind of answers your question, but so this is kind of the kind of the constraints the solver is going to find. No two horizontal ones on top of each other, which really reduces the search space, and at some point the search space becomes easy. No, there are, and so the first thing when I run the solver, and it was kind of the first thing it said is, okay, there cannot be a horizontal domino here. That is the first clause it says, so a unit clause. And I was thinking, what? Why is it? Is that the first thing the solver learns? But then it says, yeah, if I put a horizontal domino here, then there must be a horizontal domino there. Otherwise, I couldn't fix. Well, then I can replace them by two vertical ones, so this one cannot be horizontal. And then the reasoning starts continuing along those lines. So we actually have proofs for this that are only consists of unit and binary clauses. So you can do everything locally. And so, but any brute force method, right, would consider all possible cases. But the solver can figure out these kind of arguments that are that turn it into a linear size proof. Any questions? Okay. Yeah. Yeah. Yes, yeah. Every line a new pair. Yeah. 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 So the argument still works no matter what the dimensions are of the grid. And even if there is, so even if it's satisfiable, so we have a chessboard, we can still do this, right? It's just that the number of satisfying assignments is really reduced, but there always is a satisfying assignment always left, right? So you get only very specific solutions, but it doesn't remove the loss. You can never remove the final solution. Yeah. So I think so. I think now all the main theorem provers want to have at least one checker, right? And so there's always somebody who figured it out. All the checkers something in particular. So, for example, the lean checker is now able to have a much more general proof framework that it can check. The KML one is actually verified until the kind of the assembly code. And so all of them have kind of some special thing to, and some of them are more performant than others. So each one of them is kind of based on the strength of the system, something in particular. But in the end, kind of they can all do the same job. Yeah. Now, I don't know, how much time do I still have? Or okay. No, but I really like the question, so keep doing that. So what are, so I want to talk about a couple of problems that for which this technology is useful in the future. And one of them is the chromatic number of the plane. So what is this problem? This has also been a kind of obsession of me, but so we have this problem that you have all the two-dimensional space with only one restriction, is that if 2 points have exactly distance 1, they cannot have the same color. Now the question is, how many colors do you need? So already in the early 50s is what's known that you need at least 4 colors. There are, you see the 7 points on the slide with 11 instances 1. And for example, if this graph cannot be colored with 3 colors, for example, if this is red, so we have red, yellow, and blue. If this is red, and then this must be yellow, blue. This also must be red. If this is red, this must be yellow, blue. This also needs to be red, but they cannot both be red. So there's no way to color it with colors. So for the 7 points, we need already 4 colors. So definitely we need it for all the points. But the other side is that we have these hexagons with an outer radius slightly less than 1. And all the points within the hexagon have the same color, and hexagons of the same color are slightly more than 1 apart. And so there are 7 colors in the hexagons, and so we need at most 7 colors. So this was already known in the 50s, and both arguments are very neat, right? Just a small graph that shows the chromatic number and this very nice styling. And people really tried to kind of push both to increase the lower bound and decrease the upper bound. And people really got close, especially got pretty close in reducing the upper bound, because you can make a tiling with 7 colors, but with the tile with the 7th color only appears 0.3% in the plane. So yeah, it looks that it almost never appears, but there's very tiny dots of the 7th color. But real progress was there in 2018 when Aubrey de Grey found a graph with 1581 vertices that has chromatic number 5. And back then I was at UT Austin, and so Aubrey de Grey, he reached out to the media. The media reached out to Scott Aronson, a colleague of mine in Austin, and he said, yeah, I don't know how I can check this result, but I'm pretty sure you can check it. And if it's correct, you can probably do much better with SAT solvers. So that's actually what I did in the weeks afterwards. I found smaller and smaller graphs with chromatic number 5. And I will try to kind of explain to you how I did this. But one of the things, and so I will give slightly more details on the next slide. But one of the nice things that we can have is we don't just have satisfying assignment, but we have these proofs of unsatisfiability. And one of the things I also made is how to minimize the proof, so given a proof, because finding a proof is difficult, but how to kind of make it as small as possible is, or very relatively, is easier. And so what I've been trying to make tools to make, given a proof, make it smaller and smaller and smaller. And once you have a small proof, so for example, for this problem, so you have a graph, you ask, can I color it with 4 colors? If the answer is no, then the chromatic number is 5 or up. Right? Try to make the proof as small as possible, and then we only look at the vertices mentioned in the proof. And those vertices must also denote a graph that is chromatic number 5 or up. And so this is actually what I did, right? So, to know that it is chromatic number 5, right? You need to find a 5 coloring, and you need to show that there is no 4 coloring, right? The first step is easy, but the reduced formula or the vertices mentioned in the proof, they are the only ones that are required to show that it has chromatic number 5 or up. And so by really reducing the size of the proofs, so not only smaller, we can find smaller and smaller graphs. And this technique works much better than what with the Gray used. from a graph of 20,000 vertices. And what he did is he just randomly dropped things until the property broke. And he did it many, many times. But find a short, you actually are much more guided towards what you actually want to do. And then you actually do things much better than trying to randomly remove until it breaks. And so this was the smallest one I came up with back in, 2021. And so this is 510 vertices. So it is, of course, vertex critical. So there's only one vertex with the fifth color, white. And one interesting thing is that if you with, so the other ones with 4 colors, the interesting thing is what you see is that you get points that are nearby each other tends to have the same color. And so you almost kind of see kind of a hexagon tiling, but then with 4 colors instead of 7. But of course you cannot, it kind of cannot work out, right? Because, so there's something, so we know it doesn't work out, but it's almost, it seems that things are forced in that way. I am hopeful that we actually can get to 6, the lower bound of 6. It seems almost impossible to get to 7. And is that I think lower bound for 6 is 24, although it's probably, I expect it to probably be maybe in the 10,000s, but the lower bound for 7 is almost 7,000. And the reason it's almost 7,000 is because of the tiling that only uses 0.3% of the plane, is that you can really kind of always ensure that you can put the graph in such a way that you avoid those little holes that have the 7th color. So I expect that maybe with 10,000 vertices, we might be able to get to chromatic 6, but it might make, we might require 1 billion vertices to get to chromatic number 7, if that's the answer. It is very symmetric. So it's 120 degrees rotation. So a threefold symmetry. So the original graph of say 20,000 vertices where I started, or I think here started with maybe 3,000, is also symmetric. Actually, it's even more symmetric. But somehow this is what the minimization gets you. So I didn't force it to be to be this rotational symmetry, but somehow that was the short argument. So if you run it many times, then this is the smallest you can get, and that turns out to be symmetric. Yeah, there's actually, there are lots of there's lots of hexagons going on. Yeah, so there's lots of hexagons with this. So there's 2 distances, 1. Yeah, so this and there's a lot of pretty pictures and how everything is constructed in the papers. Yeah. So, but so actually I am now able to deal with graphs that are up to 1 million vertices. But the challenge is how to figure out how to put the points in such a way that you can get chromatic number 6. So I think there might be graphs with 10,000 that have this property. But also I'm talking with some people to, okay, can maybe machine learning maybe make some suggestions where the 1 million points should be, such that we have 10,000 of them that actually have chromatic number 6. Because the best thing I can do is kind of to do a static thing, but I think there might be educated guess generate points with a high density of edges, gives you can get us to chromatic number 6. Let me also briefly talk about here. This is so optimal matrix multiplication. So so the naive way of doing is n cubed, right? But so the is but to the power 3. But so Strassen tried to prove that 8 multiplications were required to do 2 by 2 matrices, but then he figured out actually you can do it with 7. And that is actually optimal, and that one is actually unique. But what is still open is, what is the optimal matrix multiplication for 3 by 3 matrices? The naive algorithm is 27. If you apply Strassen twice, it's 25. Laderman in 76 made a scheme that only uses 23. In that paper, he gave it, and he says he wrote that he will describe how he found it in the next paper, but that next paper never materialized. People are still guessing how he did it. The lower bound is 19, and if we want to beat Strassen if you want to put it in larger components of larger matrices, then we should actually. So we also applied satisfiability solving for this. So 3 other schemes were known for the decades that were different. We run a SAT solver. It produced 13,000 non-isomorphic other schemes. And we expect there probably to be millions, but no scheme of 22 has been found, and I'm starting to believe that none of them exist. You might have seen this article, is that Google's DeepMind was able also so applied their technology to matrix multiplication. And that was in this article. But so my co-author of over here, he did some automated reasoning tool in a day, and he was actually able to improve it in days. He was able to beat their results without using any machine learning, and just using plain old kind of symbolic AI. And I'm also looking into kind of, can we further improve this kind of using SAT? And questions is here, okay, where can machine learning is really shine, and where can automated reasoning or symbolic AI shine? And for this problem, I still think that actually symbolic AI works better than the machine learning. But of course, there's lots of other things where the machine learning works better. Yes. Yeah. Yeah. So, right. This is still very, very far away from the omega, right? But but in order to achieve the omega, right, the dimensions of the matrix needs to be larger than the number of particles in the universe, right? So the key question, so for where we can help, is try to get the omega in practice to as small as possible. Yeah. But yeah, it doesn't say anything about this asymptotic, although the asymptotic, it's more the other way around. It suggests that if the matrix becomes larger and larger, right, then you should be able to use fewer and fewer multiplications. And so this might be less than 23, right? But this is still, we don't know when you really start to get close to the omega, even assuming that the omega is optimal. So There's really no clear expectation of how sharp the drop will be from from what we have now to that in practice. Now, another problem that I looked into is Collatz conjecture. So Collatz conjecture says that you give an arbitrary number. If it's even, you divide it by 2. If it's odd, you do it times 3 plus 1. Then it becomes even and you divide it by 2. And if you give an arbitrary number and you apply this again and again and again and again, will you always reach 1? Right? So for example, we start with 3, right? It's odd, times 3 plus 1 is 10, divided by 2 is 5, times 3 plus 1 is 16, and then we divide it by 2 again until we reach 1. Right? Okay, so this is way beyond NP. So how are we going to try to use satisfiability solving for this, right? I will talk about it in the coming slides. So, but what we're trying to find is a function, an arbitrary function that takes a number as input, and then the function value for n should always be larger than the function value of the next number in the Collatz sequence. And if the number and the function, if it's non-negative, then if it always goes down and it's never negative, at some point it will terminate. Right? And so the question is, can we find such a function? And so kind of concrete for a limited size, right? We want maybe to have a function that if we 5, 4, 8, 3, 4, 2, 2, 1, and 1, 0. Can we find such a function? So this might like a kind of a crazy question, but we, so together with my students Emre and Scott Aronson, we looked into this and we translated the Collatz conjecture into a rewriting system that terminates if and only if the Collatz conjecture holds. So the rewrite system uses 7 symbols and 11 rewrite rules. So the numbers in the show kind of the natural kind of interpretation of the symbols. So for example, if the sequence ends with times 2 plus 1 times 1, then we divide it by 2, and this is do it times 3 plus 1. And so we have our sequence, the rewrite rules over here, and here I just show you if we can go from 27, which is 1 times 3 times 3 times 3 times 1. What are the steps? And there's many steps to go from 27 to 1, but you see how the rewrite system would eventually get here to 1 times 1. There are strings of symbols, and so this is one way of interpreting it, but it's kind of more kind of a label of it. So the key thing here is that in the termination community, so if you want to prove termination of rewrite systems, satisfiability solving is the key technique to do this. And how you do this is you ask for a function that shows termination. And you ask for a function that has a certain shape. And if the solver says, yes, I found such a function, you're happy, you're done, because now you have a termination proof. If the formula is unsatisfiable, it only means that there is no function of that shape that shows you termination. Right? And so you're kind of using this kind of NP technology to try to solve undecidable problems. And you just try to be lucky, right? That you find a shape such that it actually works. Now, are the successes. So of course we didn't solve Collatz, otherwise you probably have heard it. So so this is not there, but what we have is that if we remove any of the 11 rules, so just we have the 10 remaining rules, then we can actually show termination of the remaining rules. And another thing is what we had, and this is all kind of variants of Collatz. One of the harder variants of Collatz that for which there is a pen and paper proof. This is a part of a 2-page proof that this terminates. So what does the Farkas variant do is that if it's n modulo 1 so if it's 1 modulo 3, then we do it -1 divided by 3, and otherwise we do Collatz. And this variant actually, but it also goes up and down, but this will terminate. But it is a non-trivial termination argument. And our tool automatically proves finds a function that shows termination. And for all in the literature, Collatz-like variants for which there is a pen and paper proof, our tool is able to find such a function using satisfiability. So that's the positive thing. Everything that there's a human proof, the tools can also find it. But then we tried our tool on all kind of smaller things. Yeah? And this was the system that is the easiest appearing system for which our tool fails. And so what does it say? So if it's 0 modulo 4, you do it times 3 divided by 4. If it's 7 modulo 8, you do it times 9 plus 1 divided by 8. And otherwise you terminate. Right? So only in 1 out of 8 cases you go slightly. Yeah? In 2 out of 8 cases you go down. And in 5 out of 8 cases you just instantly stop. That so if you try to do this for any number, the number of steps that you can get, it seems to be at most the logarithmic of the number. But proving termination is very difficult. So I actually gave it to Terry Tao. I said, okay, can you prove termination of this? So, and he looked at it for a while, and at some point he said, he expects that this is as hard as Collatz. So he says, actually, this reduces to a special case of Baker's theorem, for which he got the Fields Medal. So he says, if you can do this automatically, that would be the basis of where Baker got his Fields Medal. So I don't expect there to be a short argument. So this is, yeah, but we offer $500. I hope I didn't discourage you, but yeah, so this seems to be a hard problem, but yeah, so I thought it was kind of cool that the solver was kind of stuck on this relatively easy appearing one, but apparently this is kind of the easiest looking one for which a proof will be very difficult. Yeah, although we don't. So the thing is, for example, we tried initially all the termination tools on this, but they all failed, and so we wrote our own solver to make sure that it was possible. So it's only our own solver based solver that is able to get these results. The existing ones were not able to get it. Yeah, no, but so we want to have something very specialized, and so they also don't consider. So yeah, I don't want to go maybe in too much detail, but so what they're looking for is so each symbol will be represented by a matrix. And valuation of the string is that you just multiply it all. And if you do a rewrite, then the multiplication, the end of the multiplication will get smaller. The existing tools, because almost in all cases for which in the use the competitions, you need to at most kind of a 4x4 or 5x5 matrix. For many of these results that we have, you need 8x8, 6x6, 7x7. And so they didn't really consider it in optimizations that you need for kind of larger ones, because apparently that's not what they're considered in their community. But we really wanted to also explore. We also tried it with 12x12 and 20x20, although these formulas would get very big and there might be no hope in solving them. But at least we tried and to make sure that we can have big problems that we can give on supercomputers. So, because I run this on many years of compute on the Amazon cloud to really try to solve these short runs. Okay, so to conclude, so satisfiability solving has been kind of a great success in solving mathematical problems, and I think there's only many more to come, especially when we, so far I already had a lot of help from mathematicians, but I also think that machine learning can be of a big help in the near future. The proofs are enormous in size, but we can fully trust them because we have these formally verified checkers. And actually, what I also mentioned earlier, we have end-to-end verification now in the linear proving system. Yeah, and what are kind of the problems that might be open for this kind of approach? So the chromatic number of the plane, matrix multiplication. Also, another thing I didn't discover here was Hadwiger-Nelson conjecture, Collatz conjecture, and without doubt, there are many more that might be open to this. So, thanks a lot.